Okay, well, we all have some things to improve upon. So let me explain to you how pressure is measured. Okay, so let me ask you, do you know what the term mad as a hatter means?
Yeah.
What is
The pins they would stick in their hats would poison them and make them like all loopy.
No.
That's what I read.
It has to do with mercury.
Yeah.
The beaver hats is what we're talking about.
So, yeah, but I think they're related to the same story.
Probably so.
Make these hats, and they have all this felt and other hair, and they want to get all the loose stuff off. So what a hatter would do was build the hat and not worry about cleaning it while he was doing it. And then he had a big barrel of mercury. And he would jam the hat down in the barrel of mercury, shake it around, and then, right? You guys know mercury is really poisonous. It's a neurotoxin. Yeah. And then they would pull it out, and they would come out perfectly clean. Eventually, the neurotoxin part of it would make them crazy, and they'd be mad as a hatter, because the guys who made hats had mercury poisoning. Okay, so why do I say this? Because we used to have a lot more mercury around. Even when I was a kid, we had mercury thermometers. And one of my early experiences, my mom was laughing about these things the other day, because she knew we were doing stuff that she didn't want to know about. She just didn't want to know about it. I didn't want to go to school one day, and I wanted to heat up my thermometer so it looked like I had a fever. I just didn't realize how careful you had to be with the mercury thermometer. So I held it over a match, and I thought it was going to heat up really slowly. It didn't. It shot to the top, it ran out of room to expand, and it blew up. It popped. Mercury's everywhere. Marginally, we could say I'm probably okay. But, yeah. Mercury everywhere. It's probably still in the sink at my mom's house because that stuff settles down to the bottom, doesn't go away. So one of the things that people discovered early on, if you get a tube of glass, I'll tell you people, and you put it in and you fill it with mercury. Oh, what did I just do? I just deleted everything I just drew? Did it disappear up there too? Oh, I don't know how I did that. It's all you're ever going to see now. So it's filled with mercury, the element. Now, the density of mercury is very high. It's about between 13 and 14 times more dense than water. Okay, so if you think about like a cup of like a 1 liter bottle weighs about a pound or so of water, that size. Mercury would be like 14 to 15 pounds just in that one bottle. So it's much more dense. But they would fill this tube up with mercury, and I always tell people it looks like a really bad drawn hat. And they would put mercury like this. Now, have you guys ever done the experiment when you were a kid? You take a bucket, you fill it with water in the swimming pool, and then you try to lift it out, and the water stays in the bucket, right, as you lift it out. And when you get it above, then what happens? The water level, all the water comes out. The reason it does that is because the air can get back in, and then it allows the water to leave the bucket. Okay. So what you do is you take this tube of mercury, and you submerge it into mercury. So literally, they would take these meter-long glass tubes, fill them up with mercury, stick their hand in, and let all the air out, and then flip it over, and then pull it out. Okay? So what would you expect to see happen? Well, what they saw happen, right, first thought would be, well, the mercury should stay all at the top, because there's no way for air to get through the glass, so it should stay all the way at the top. In fact, what it does is it falls to a distance that's always about the same. It's about 760 millimeters. If the air pressure, so the question is, what's up in the top? Yeah, the answer is nothing. It's a vacuum. And so literally, the mercury has enough force behind it to create a vacuum, and in a vacuum there's nothing. Okay? And so when you're measuring pressure, you think about that, there's a vacuum here. That means the force of the mercury pushing down equals the force of the air trying to make its way back in. So you think about a pressure of air that's pushing down like this, and the pressure of the mercury pushing down like that. Those counteract each other, and it just happens to be when this height is 760 millimeters, which is 76 centimeters, that high, it stops moving most of the time. That's like most, like old school barometers were always about a meter long, okay? So what good is this? Well, this is what they said is 1 atmosphere. So if you had 760 millimeters of mercury supported by an external pressure out here, they would call that 1 atmosphere. If the pressure goes up on the outside, what do you think the mercury will do? If the pressure on the outside goes, there's more pressure on the outside, what do you think the mercury should go up? Because now there's more force out here, so it could support more weight in the mercury, and the mercury goes up. So the nice thing is when the air pressure on the outside goes up, the mercury goes up. When the air pressure on the outside goes down, the mercury goes down. So that's why when you look at the weather report, like type Fresno B weather, and you look at it, they'll tell you like today it's like 29.9 something inches of mercury, because we're still on the English system, but that turns out to be roughly around 760 millimeters. You expect weather changes when there's big swings in air pressure. Because remember we talked about pressure is created by molecules, right? The number of moles. So if the pressure's lower, there's a region in space, in that low pressure region, where there's less molecules bouncing around. And so the air will tend to move, the high pressure will tend to move to the low pressure. And that's what causes weather fronts, which causes like big clouds and stuff to move around. So that's why people in the valley are always like worried about, well, what's the air pressure today, right? Because they look at the air pressure, they can tell in the winter, like, oh, a storm might be coming, because when the pressure drops, that means a low pressure system's coming through. It usually brings rain and stuff with it and that kind of stuff. So they measure that using a barometer. My uncle, Joe, who was the really practical one, he would look at the mountains, and he could tell what the air pressure was by how far the clouds were up on the mountains in the Sierras. He would go, oh yes, the air pressure's pretty high. I'd be like, what are you talking about? He'd be looking at the mountains. And he could tell just by doing that. And when I was a kid, we always knew that you would go fishing when the pressure was low. So we would look at the weather and say, oh, the air pressure's low today. We should go fishing, right? Actually, I said that every day. I went fishing a lot. I talk about it a lot now, but I don't do so much of it. Okay, so these are all, we talked about pressure a little bit. That's how you measure it. These are all equivalents to 1 atmosphere pressure. So you could consider all of these, okay, as conversion factors for different pressure units. So, for example, in PSI, it's 14.7 PSI is equal to 1 atmosphere. Or this one, 760 millimeters of mercury, that's 1 atmosphere. So that's how they got that unit. It was measured empirically that, oh, it will support this much mercury. We'll just call it an atmosphere, and that's kind of where we got it. Now, millimeter of mercury isn't somebody's name, right? There's nobody named Mama Hugga. That's what that says, right? Mama Hugga. No? All right. See, I told this chemistry joke, and there was, you know, the rest of the joke. But there is a guy named Torricelli, and so in honor of him and all his work working with gases, they named a millimeter of mercury and a torr are the same thing now. So 760 millimeters of mercury is the same as 760 torr. Okay? Which is kind of an insult because it's such a small unit, right? Oh, you're famous. We're going to name this really tiny unit after you. Sorry. Let's see, did I do that next problem? The tire pressure, did I get to do any conversions and stuff? No? Yes? No?
No, we do.
Okay. Sorry, I just explain concepts. Okay, so I'm going to just, this is slightly different than the version you have because I didn't have time to download the version you have. This is just what I have on the computer. But it's pretty much the same. So your tire air pressure is 35 psi, right? How many pascals, that's another pressure unit, or atmospheres does this represent? So the calculation's pretty straightforward. It says 35 psi, so I want the pressure, that's 35 psi, and I can convert that as 14.7 psi per atmosphere. And you can do that calculation. You get slightly over 2. Let me grab my calculator. Or slightly under 2, sorry. I think it's slightly under 2. No, slightly over 2. So 35 divided by 14.7, 2.38. So ATMs. Sig figs, 2.4. Because the 35 has 2 in it. What did I say the pressure for the day was, actually? And the next part, I didn't, it says...
29.97.
Yeah, so I actually looked on the FresnoB.com site. It said the air pressure is 29.97 inches of mercury. Oh, by the way, I forgot to do that other part of the problem. I'll get back to that in a second. I just wanted to explain this conversion. You notice there isn't an inches of mercury to millimeters of mercury conversion factor because it's the same as inches to millimeters. Okay, so I'm going to do the calculation. I'm going to use some of this space on the side because I gave you more space than I actually have. If I want to convert this into millimeters of mercury, then the way that you do it is you do it like this. I'll show at the bottom. 29.97 inches. And ignore the mercury because you're converting the inches to millimeters. There's 2.54 centimeters in an inch. So I'm doing that metric conversion stuff. That's supposed to be an inch. And how many millimeters are in a centimeter? You guys remember? 10 millimeters in a centimeter. You can calculate that out. Some of us old guys know that it's actually 25.4, and you just do that. But so 29.97 times 2.54 times 10. So the pressure on that day with 4 sig figs is 761.2. millimeters of mercury now. Originally it was inches in mercury. I didn't convert the mercury part. I just converted the length part. Right? If you're really lazy, they're both the mercury. If you're really lazy, you look up 29.97, which is 30, and you flip the yardstick over, and it's about 761. Because, right, it's on the same, yeah, that's what you can do if you're lazy. But you're not lazy because I'm going to make you calculate it. So, okay, just real quick aside. Directly proportional and inversely proportional, okay? So what does directly proportional mean? You're kind of equivalent, but if one goes up, what does the other one do? The other one goes up, right? So proportionality pressure and moles are directly proportional to each other. So we can say pressure is proportional to moles. Now that makes an assumption, okay? And the assumption is that temperature and volume are constant. So that means you have a container, it's a certain size, okay? And you're not letting the temperature change, or you're letting it come back to room temperature. And you're pumping gas into it, or you're pumping gas out of it. So when you pump gas into the container, the pressure does what? Goes up, right? If you pull gas out of the container, the pressure will go down, right? So this is what we mean by directly proportional. So there's an interesting thing that the old scientists did. The guys like, their names like Boyle and Torricelli and these guys, right? What they did is they recognized that when you have something that's directly proportional, you can write an equation out of it. You can say pressure is equal to a constant times the number of moles. And then they would actually do experiments to determine what that constant was under different conditions. But as long as the volume was the same, and as long as the temperature was the same at which they measured the pressure, that equation was true.
So the constant was constant.
The constant was constant as long as
You kept
the volume and temperature are the same, okay? So what is, and if you graph something like this, in principle, right, it looks like this. You know y is equal to mx plus b? Remember y is equal to mx? This is y. This is mx and plus b. Well, this is plus 0. So it goes through 0. This is, on this axis, moles, and this axis, pressure. And what does K represent? It represents the slope of this line. Okay? And it turns out any 2 points could be related to each other if you know the equation for the line. So if you know the pressure and moles at one set of conditions, that if you know the pressure and moles down here, if you know the slope of this line, you could calculate the pressure and moles at this set of conditions, just knowing the slope. So if I gave you moles, then you can calculate pressure, for example. Okay? I'm going to work this up one more step. And the one more step is this. If you take this simple equation that I have here, that pressure is equal to K times the number of moles, I can say pressure divided by moles is a constant. So if I have the pressure and moles under one set of conditions, that's equal to a constant. It's also equal to the pressure and the moles under another set of conditions. And you'll see when we do a lot of the calculations in this chapter, we're basically manipulating proportions based on directly and indirect proportionalities. The equation's real easy, as it turns out. The guys in the morning class got the equation. All you have to do is remember the equation, plug stuff in. But the way they got it is this, okay? They derived that equation using these proportionalities. Now, the other thing that I wanted to point out about this is a lot of the empirical gas laws, all that stuff that they observed, you can predict the outcome because you know, like I just said, you have a cylinder and you pump gas into it, what happens to the pressure? It should go up. If you have a cylinder, you take gas out of it, what happens to the pressure? It goes down. It's always based on the proportion of the moles. So you can actually do these calculations without ever solving an equation, just knowing it's proportional to these different factors and plugging numbers in, okay? So I'm going to show you a little bit of both of that. Most people just want to do the equation, okay? But you can avoid doing the equation just by plugging the proportions in the way you expect the gas to behave, okay? All right. Inversely proportional. So what does that mean? When one value goes up, the other value goes down, right? Turns out pressure and volume are inversely proportional to each other. So that means I can say pressure is proportional to 1 over volume. That's what the inversely means, 1 divided by, okay? So that's an inverse proportionality. So I can make an equation out of this one too. How do I do it? I stuff a K in there, and I call it equals, okay? So I could say pressure is proportional or equal to, sorry, K divided by volume. And again, you can make graphs like this, but they don't look pretty like straight lines. They start high here and they make this sort of shape like this. They have that. That's an inverse proportionality curve. That is, as your pressure gets, this is your volume, let's say, or pressure. Let's see, do I want to do volume? I do volume here and pressure here. As your volume gets large, your pressure is low. As your volume gets small, your pressure is high. Well, you kind of know that because if I gave you like a syringe, right, and you plugged up one end, and you let it fill with air first, and then you pushed it together, the volume would be getting smaller, right? What would happen to the force that you would need to push the syringe barrel in? Yeah, it's going to be a lot more harder to push it in if you're not letting anything out, right? Of course, that's how syringes work. Because you squeeze it, you create a pressure on the inside, and that liquid shoots out, right? But if you don't let it come out, if you squeeze the volume so that it gets smaller, the pressure goes up. So you know intuitively it's inversely proportional, okay? You know this behavior. Now, you may not know this graph. That is not intuitive. Intuitive is like if I took the barrel, right, and I pulled it out, what would happen to the pressure on the inside? It should drop. It decreases. You know that because when you let go of it, it shoots back in, right? Okay, I've done all these things. Right. I'm not saying go out and get yourself a bunch of syringes, but it is kind of fun to play with syringes and make things with them. It's kind of a chemist trait. Okay, similar, it's a constant. So I could say P1 and V1 is equal to a constant. So that's maybe the pressure and volume here on the graph, right, is equal to P2 and V2. That's a different set over here. But they're all related to each other by a constant. The assumption is, though, if this is going to be true, right, temperature couldn't have changed and moles can't change. Because if those things change, then everything kind of is thrown off. Like if you have a leaky syringe, for example. That would throw your thing off. Okay. Oh, do you need that up still? Sorry. In a little hurry. I'll take a sip of coffee. Helps me relax. Sound like math so far? Most of this chapter is just like math. Right? And you need to know this term, directly proportional, and pressure in moles, and what it means to be directly proportional. Like in the equation, they're like equal to each other. And inversely proportional means it's inverse, like one over the other. You need to understand those terms. Those are the kinds of questions you get about, oh, is the pressure and volume, are they inversely or directly proportional? You get those kinds of questions, okay? So you need to understand that part. But for the most part, you get the set of equations that you use. There's only really two that you use. You just use them over and over and over again. Okay. So I want to start by talking about what are called the empirical gas laws. And I gave you a lot more room to write, I think. But maybe not. I'm about to say, okay. Oh, maybe I posted the wrong ones. I spent a lot of time editing this so that you'd have more space, but maybe I blew it. Okay. There are things called state variables for gas. And for a gas, the pressure, volume, temperature, and moles. Okay. And if you know those things about a gas, an ideal gas, we talked about ideal gases the other day. You know everything about a gas. You can define the gas to some crazy level of precision. Okay. State variables tell us about the state of a gas. Now, that's kind of a vague, nebulous thing, right? But your net worth is like your condition. It's your state. So how do you know your net worth? Yeah, most of us can say 0 or negative, right? But you look at your bank account, right? You look at your income, you look at your expenses, you look at all your holdings, your assets, your home, your cars, and you take all that and you add it up. Each one of those is like a state variable for your net worth. And your state is your net worth. Right? So if you want to know what you are worth money-wise, and as you get older, you're supposed to figure these things out. Hasn't happened yet. Don't know. I've got too many kids. I just know I'm in debt. So, college, you guys know that what you're doing here is such a good thing because it's such a good education for so little money. Honestly, it is the best way to go. Sorry. Of course, I work at a community college, so I would say that. But my son's first year at community college was basically free. And then every year after that was about $15,000, and that's cheap. My son at Santa Cruz, it's $35,000 a year. Yeah. Just makes your eyeballs expand. But the good news is he's done next year, and I only have 4 more. That's not why I teach this class, by the way. I was not going to work this summer, but they needed somebody to teach. I just teach this class because I like teaching this class. Otherwise, I don't ever get to teach it. So, sorry. So state variables, you get the idea what they are? They tell you about the condition of the gas. And so just like how much your house is worth, how much your stocks are worth, if you have any, things like that, your bank account tells you about the condition of your finances. The same thing is true for gases. So a long time ago, there was these guys. I will write their names out, but it's not important other than you should know who did these things, okay? Boyle. He related pressure and volume. Avogadro. He did quantity of substance and volume. Let's see, Boyle, Avogadro, Charles. He did volume and temperature, actually, if you keep the pressure constant. And you can kind of see where this is going. What these guys did is says, well, I'm going to study pressure and temperature, so T and N have to be held constant. Avogadro, I'm going to study N and V, so P and T had to be constant. Right? And each one of these was a proportionality law, like pressure is inversely proportional to volume. Avogadro was moles is directly proportional to volume. And Charles was volume is directly proportional to temperature. Now, you knew that already, right? You take a balloon or even like a potato chip bag and you stick it in your car in the summer, when you come back out, it's like really taut, right? And that's because as the temperature increases, the volume of the gas increases, so you kind of knew that that's the way that happens, okay? There's more of these, because for every 2 variables, you can define a new law, and they did, okay? But these are the ones that are principally important for you to like be familiar with. What it came down to, though, in the end, is that they found that the pressure and the volume is equal to the moles times R times T. And R is that K from the other equations, but it's all of them combined. So they found out that you could relate the state of a gas from one state to another simply by using this proportionality constant here. And this is true for almost all gases under all conditions, because gases behave ideally most of the time. And this is known as the ideal gas law.
So then it doesn't matter what gas it is.
Well, and that's the thing, right? It says moles of a gas, right? It doesn't say grams of a gas. It says moles of a gas. But it only matters what the gas molecules, how many there are.
That's right.
The,
What they-
Not the mass.
and not the mass. And yeah, it's kind of weird. So think about it like this. If I filled,
There's a different room.
I have, imagine, I usually have balloons too. I don't have any balloons today. Balloons are great. If I had a helium balloon that was this big, okay, what would it do? It floats, right? That's why you buy helium balloons.
Sure.
Nobody buys an air balloon because what does a full of air balloon do?
Sits on the floor.
It sits on the floor. It's not very fun, right? So here's the deal. Why does the air balloon sink when the helium balloon floats, right? Well, air has a density, right? Because the balloons are the same size, there's the same number of particles in each balloon. It doesn't matter that this one's filled with helium or this one's filled with, let's say, mostly nitrogen. But what's the difference between a molecule of helium and a molecule of nitrogen? Yeah, helium's a lot lighter, right? A molecule of helium weighs, for every mole, okay, about 4 grams. Now, if you take a balloon and it's about this big, it has 4 grams of helium in it. That's about a mole of gas. It's about that big. It's 22.4 liters, 23 liters. Okay, so the other way to, this is how we relate to things. It's 11 bottles of soda. That's, if you drank them all and you sat them down, the container would have about a mole of gas in it. So a helium balloon that's this big, that's about 22 liters, okay, will be 4 grams. But a nitrogen balloon, that same size, same number of particles, will have 28 grams in it. And because it's the same density or more dense than air is, right, and the balloon weighs something, it sinks in the air. But because the helium has such low density, has such low mass, it floats in the air. It's just like a piece of wood. If you took a piece of wood and you put it in water, generally wood tends to do what in water? It floats because it's less dense than water. Guess what happens when you stick ironwood in water? Guess. It sinks.
Yes.
Why is it called ironwood?
There's iron in it?
No, there's no iron in it. It's just really dense. It takes hundreds of years for these trees to grow to a certain size. A long time. So it's just a really dense wood, but it's more dense than water is. So it's the analogy is like the air balloon is like the ironwood, sinks in the air, whereas the helium balloon is like regular wood. It floats in the air, wants to keep going up. It eventually stops rising. Usually it blows up, but eventually it would stop rising. Okay. So that's the idea.
It expands as it rises.
Yeah, and cools too, though. So there's a bunch of things going on. All right. So, real quickly, if I said P1, V1 is equal to R, and isolate R as like it's a variable, that's N1 and T1, right? You see how I did that? And that's going to be equal to what? It's going to be equal to R, and then P2, V2, N2, and T2. It's going to look like that. And then that's, I think that equation is ugly, so I rearrange it, okay? And this is one of those equations you need to know. The first one is this one, the ideal gas law. The other one is this one, and this is what we're going to use for the problem. P1, V1 over P2, V2 is equal to N1, T1 over N2, T2. And the reason the R is not in this second equation is because I set them both equal to R and then I rearranged the equation and I end up with this. So the way I generally tell people you have to deal with these problems, okay, is you make a table. And the table will tell you which problem you're dealing with when you actually go to solve the equation. Okay? So the table is going to look like this one. And the table actually is the equation. So I'm going to go like this. There's not nearly enough room here. I meant to make a lot more room under each one of these, but I messed up. So P1, V, or sorry, P, sorry, not 1, V, N, and T. And then I have state 1 and state 2. And you notice why I say this table is the equation, because it's like it has the equals sign here. This is what? Pressure 1. This is volume 1, so there's P1 and V1, are equal to, right, N1 and T1, that's N1 and that's T1, divided by P2, V2, N2, and T2. Okay? So when you solve these problems, okay, what you do is you read the question and you just start writing the information in the table. And when you're done filling in the table, it'll tell you, do I need to use this? Or do I need to use this? And eventually you'll get the idea of like just looking at the wording of the question and be able to start the problem. But until you get there, I always suggest you start a table like this, and the table will tell you what kind of problem it is. Okay? So I'm going to do one from here, and then I'm going to skip down, and I'll do one from later on, just so you can see the comparison of the two. So for this one, right, it says, if a gas has a volume of 255 centimeters cubed at 725 millimeters of mercury, what is the volume at 760 millimeters of mercury? So now what you have to do is be able to group the variables together in terms of their states. So the 255 centimeters cubed, what is that? Volume, right? And so I'm going to call that V1 because it has that at a certain time, right? So I'm just going to call it V1. By the way, if you put it as V2, right, and then this would be P2, so then you would just put both of them down here, and you get the same answer to the problem. So you can't accidentally assign one to P1 and V1 incorrectly as long as you're consistent. You'll still get the same answer. So what is 725 millimeters of mercury? This part right here. That's the pressure, right? So that's the pressure with this volume, though, right? So that should go here. So that's going to be 725. And then it says, what is the volume at 760 millimeters of mercury? So what's 760 millimeters of mercury? It's pressure 2. It's the second set of pressures. So 760 goes here. So if I had you look at that and say, what's missing? Like one of these squares is not like the other. You know that game? Which square is not like the other? V2. V2. What are you looking for? Volume, yeah. So you didn't actually, it could have just said, calculate the thing that's missing. The thing that's missing is the thing that's not like the others. There's data missing here. So this is what I'm going to tell you. Whenever you have filled in two states for a gas, and you have values in both, you're going to use this equation. Okay? So take that on faith. I have two states. I have this and this. The other thing I don't have any of this information. Okay? I'm going to talk about that in a second. But this is the way the table looks if you're doing what's called the change of state problem. These are empirical gas law problems. Now this gas law has a name. It's called Boyle's law because Boyle related pressure and volume. Okay, but so we're doing a Boyle's gas law problem. So now what's left? Well, what did it say about the moles in the problem? Nothing. It didn't even imply a gas amount, right? So I'm going to assume this, that the moles are the same. At the beginning, and at the end. What did it say about the temperature? Nothing, right? So I'm going to assume that the temperature at the beginning and the temperature at the end are the same. So T1 is equal to T2, and N1 is equal to N2. What does this equation do if N1 is equal to N2? They cancel. Simplify, right? And if T1 is equal to T2, that simplifies out as well, right? And what you're left with, and people hate this part, you're left with P1 V1 over P2 V2 is equal to 1. Don't say 0. It happens all the time, but don't say 0. It's 1. It's simplified. It didn't disappear, right? So that's equal to 1. I'm solving for V2. All I need is to plug it. I need to rearrange this equation and then solve it for V2. Okay. To make my life easy, I'm just going to solve it for V2. We can go over the mechanics of this solving it for V2 in class later. The guys in the morning lab already solved this many, many times. Equivalently, I should say. Okay. And I'm assuming that this canceled because nothing was said about it. So I'm just going to mark it off like that. So rather than remembering Boyle's law, if you can just read the question, you can interpret Boyle's law out of this. If I tell you Boyle's law studied the relationship between pressure and volume, you should be able to derive Boyle's law because you should be able to cancel these out and then rearrange. This is Boyle's law here, what's left, okay? P1 V1 is equal to P2 V2, that's Boyle's law. Or pressure is inversely proportional to volume, however you want to say it. Okay, so I'm going to plug numbers in. And as long as the units are the same, right, you don't have to convert them over. As long as the units from here to here are the same, or here to here are the same. The only time that's different is when you do temperature. It has to be Kelvin, okay? So, okay, what am I left with doing here? I have to put in 725, that's pressure 1, right, so that'll go here. 255 is volume 1, so that'll go here. And I'm going to divide by 760, so that'll go there, and that should give me my new volume, okay? I don't know if I have room to get everything in there with units. Well, let's try it. 725. I'm just going to say millimeters times 255. This is milliliters, right? Centimeters cubed? Centimeters cubed. Oops. Centimeters cubed. Ran out of space. Sorry, guys. I could have written off the edge, I suppose. Divided by 760 millimeters. And that's in millimeters of mercury. Sorry, system went to sleep. Please don't make me log back in. Oh, good. Okay. And you calculate? What'd you get? Somebody do it already? Nice. $725, right, times 255 divided by 760.
Less than
243.
Is it, I got 225.
centimeters,
Or 250,
cubic centimeters, volume.
What'd you get? 225?
I thought I did.
Okay. Ha! I was right for a change. 2.6 figs because of the 760 was, even though it sounds like it's exact, it's 2 sig figs. So 240 centimeters cubed. Okay. Now notice the interesting thing that happens in a lot of these calculations. The millimeters cancel out, so these units just canceled out nice and cleanly. The reason that's kind of cool is because as long as they're the same, they cancel. So they didn't have to be in liters. What you're going to find out in the next problem that we do, everything has to be in certain units. But in these problems, not everything has to be, just because they cancel. Okay. Kind of get the idea how to do this? Because I'm going to come back and do the next problem, okay? But what I want to show you is the other kind of problem, so you can help sort them out in your head. When you look at them, you'll know which kind of problem it is based on how the table fills in, okay? So let me go down and get to the next problem. And then I'm going to, oh, I just realized I could cheat. I just made the space a lot bigger for me. Sorry, guys. This is really how I should do this. I should do this once and then. Normally, I don't show you guys. This is what I like type, and then I make slides from this. But I didn't ever make the slides for Chem 3A because I just like talking about it. So there's no pretty pictures. The slides I show you guys are the ones I stole from my wife. Okay. A cylinder contains. So I'm going to make my little table. I go P, B, N, and T. I go 1 and 2. Okay. Oh, I should have made it bigger. Oh, it's 35 psi. So that's 35, right? Pressure. At 26.5 degrees Celsius, am I just identifying like what the variables are? And 1.5 moles. That's PSI. I'm going to write underneath what the pressure units are, PSI. So you notice something weird about the table? What did the last problem do? The last problem actually gave us two states. They said, well, at this state it's this. What is it at this other state? These problems don't do that. So what you do for these problems is you just use PV is equal to nRT. It's an ideal gas law problem. I often call these like the first type of problem, and there's the second type of problems. There's type 1s and type 2s, but I just make that up as I go along. Some years it's the other way around, so it's the way I am. So what this says to me then is I could calculate, you notice how many unknowns are in this equation? Well, there's 4, because R is a constant. It's the same for every gas. Since there's 4 unknowns, right, I need to know 3 of them before I can solve it. And since there's 4, and I've given 3 here, what can you solve for? You can solve for this one, right? What are they asking you for? What's the volume of the container? Right, again, they didn't have to tell you that almost, because the way the problem lays out, it's the only thing that's not there. And so you can figure it out from that. Okay, so I'm going to solve this equation for volume, and then I'm going to give you the warning. And this is just the units warning. Make sure your units match, okay? It's a good rule in life. So what do I mean by make sure your units match? The value for R is 0.08206 liters times atmospheres per mole times Kelvin. all the way over there. I squeezed it all in there. Oh, sorry. A little bit messy. Move it over a little bit. So what does that mean? It means that my units for my pressure have to be in atmospheres, because I'm going to use the R constant with it. And for it to work, the units have to match. All right? 1.5 moles has to be in moles, so it's already in moles, so that part's good. And 26.5 degrees Celsius, it has to be in Kelvin. So to go from Celsius to Kelvin, you always just add 273.15. Okay? Now, if you add 273 to it, it'll still work out. But the actual number is like 273.156. It goes on for like many, 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 many decimal places. Okay?
Where'd you get that number from?
R?
Yeah.
So remember I talked about you make a graph and a proportionality constant?
Yeah.
It comes from experimentation.
Yes.
Well, actually, you can calculate it too. You can derive it empiric like that.
So this is just like a known number?
Yeah, it's just like a
Okay.
given, and on every exam, it's actually been on every exam, last few exams. It's in the front, R equals, and
Okay.
yeah, yeah, but it takes experiments to figure it out.
That's right, you take the 4 of them, you gotta have all 4 of them,
Yeah,
and then you put it in the relationship PV.
it's a four-dimensional graph, I guess.
Well, it's just a fraction.
I don't know, I understand. Makes my head hurt. Okay, but they get R that way. Okay. So, oh, I get it. I know, but you just have to remember that's given, constant. But it comes from a graph, which is really kind of cool. It does come from a graph. Okay, sorry. So now, pressure. I need to convert that over to what? ATMs. Yeah. So it's 35 psi, 14.7 psi for every 1 atmosphere. Now, our unit conversion table, the one I gave you, the periodic table on the back, used to be really awesome and had to do all these pressure conversions, but they basically hacked it up in the last iteration, so a lot of these things are missing now, so I'm going to have to petition that they put some of those things back. So 35 divided by 14.7, that's 2.38. 0.95 ATMs.
Do you have to put that in the
No, how many sig figs are going to be in the answer? Only 2, right?
You don't want to.
So those other ones are really not necessary, but you want to keep some of them so you don't get rounding errors in your calculations. All right, so keep a few extra. I should have probably just kept like an 8.1 instead of an 8.095. But I wasn't thinking about how many were in the original number. I just wrote what my calculator told me. That's all I did. Okay, 1.5 moles is okay. 26.5 degrees Celsius. To get it into Kelvin, just add 273 to it. And I like doing the 273.15, so I go 273.15 plus 26.5. That's 299.65. 300-ish, but call it 299.65. One of the things, and that's Kelvin, one of the things I want to warn you about, when you do this conversion, 3 sig figs, 5 sig figs, remember it's to the place, so there's actually 4 sig figs. Lots of time when you do Kelvin conversions, you end up picking up a significant figure. It doesn't affect us in this calculation because this one's only 2, but I want you to recognize that there's 4 in here because this one is to the 10th, but you're adding a place here, so when you look at that, there's 4 sig figs there, okay? So do I have everything I need? All right, moles is in moles. So I'm going to plug everything in. Pressure is now in atmospheres. Temperature is now in Kelvin. So now I can say volume, sorry. And I'm going to plug in moles, which is 1.5. I'm going to make my pen a little skinnier.
I let my kids color on this on the weekends, so the pen tip gets really fat. 1.5 moles. Then what? 0.08206, and then I'm going to put the units, liters times atmospheres for every mole times Kelvin. And then I got to multiply by temperature, right? Sorry, I just realized it's going up. 299.65 Kelvin. And on the bottom, I have 2.38095 atmospheres. With only 2 sig figs. So I'm going to end up rounding the whole thing to 2 sig figs. Take my handy dandy calculator. 1.5 times 0.08206 times 299.65 divided by 2.38095. 15.49 49126. Gosh, what are the units? Liters. Now, remember, as long as you use all the other units to match what's in R, the thing you're solving for will come out in the units that you didn't use, right? Like the only ones you didn't use in this one are liters. So I put in atmospheres, I put in moles, I put in Kelvin, so the volume will come out in liters, okay? You can see that if you cancel it. So moles cancels with moles, Kelvin cancels with Kelvin, and atmospheres cancels with atmospheres, and you're left with liters. Okay. The reason it's important for you to match the units is so that the answer has units that you expect rather than some other weird thing. Okay.
Did you get the sig figs from the 1.5 mole?
Yeah, from the 1.5 mole. So when this rounds, I was letting people stew over it. What does it round to?
15.5.
15.
So it's not 0.5, it's just 15.
Yeah, because it's 2 sig figs, and it's not 16. All right, a lot of people make the 16 because they're like, oh, there's a 9 here, so that's a 5, so that's a 5, that's a 6, right? But that's just a 4. You don't look at this digit, right? It's one of the things that worked out nicely about this problem. 15 liters. Okay, so think about this, okay? Just a number to remember, okay? The volume of 1 mole of gas, it doesn't matter what the gas is around 20 liters per mole. Ballpark. It's more precise number, 22.41, and then you have to specify temperature and pressure, okay? But 1 mole of gas occupies about 20 liters. Well, I have 1.5 moles of gas. Okay, that's at 1 atmosphere pressure, but that's more than 1 atmosphere pressure. It's 2.3 atmospheres of pressure. So, but the fact that it's around 15 liters falls in that category of got a little bit more moles, a little bit higher pressure. It's going to still be around 20 ballpark. So you can estimate your answer being in the right range just knowing about 20 liters per mole. If the pressure is double, if it's 2 atmospheres, then it's 10 liters per mole. Okay? That's because pressure and volume are inversely proportional. Okay, so anyways, you see how this table filled out? Filled out differently than the first one? Ideal gas law problem. Okay, you'll get used to, eventually you'll read a problem and go, oh, that's an ideal gas law problem. But until you do that, just write this table every time and put numbers in it. It seems like a waste, but you will not miss problems when you do that. And then when you get used to it, you won't need the table. Honestly, I still use the table because I miss those little details sometimes.
It's kind of like adding that way either.
Let's do this one. Temperature of a gas increases from 25 to 125 degrees Celsius and had an initial volume of 25 milliliters. What's its final volume? So let's do this real quickly. I'll make my little table. I'm going to make it bigger. Put my states in. Go P, V, N, and T. And I'm going to start filling stuff in, but you can already tell there's not that much data there, so I'm not going to fill the whole table in. But I have to figure out whether or not it's an ideal gas law or an empirical gas law problem. Okay. Okay, so I have 25 and 125. So it goes from 25 to 125. So I'm going to make T1 25 and T2 125. Make sense? So, and it initially had a volume of 25 mils. So where does the 25 mils go?
I'm one, V.
All right, V1. So I'm going to fill in V1. So that's 25 degrees Celsius, degrees Celsius. So what am I solving for? All right, I'm solving for V2. And what is it asking for? The final volume. So that's where it kind of... So what do I have? I have no information about pressure, no information about moles. So this is not an ideal gas law problem. It's an empirical gas law problem. Charles law. So I can say my equation, I'm just going to write the whole thing out again. Again, write this out every time. Just because if you do about 10 of these problems, you won't have to try to memorize it because you will have memorized it. It will just be like, oh, of course this is what I write. So what do I get to cancel?
The N, so the N's
Ends.
and P's.
And I'm solving for V2, okay? So V2 is going to, the simple way to solve, like this one for a lot of people is complicated because V is in the bottom that they're looking for, is to cross multiply. Get rid of the denominator and just be left with the numerator. So basically, you're going to go like this. V1T2 is equal to V2T1, and then isolate V2. So just divide through by T1. So I get V1T2 over T1, like that, okay? So that's not this class, but definitely if you have problems with this, you got to be able to do it to like do the problems. So you need to talk to me if you're having these problems, because I can just give you problem after problem to solve. Isolate this, isolate this, isolate. Given this, this, and this, isolate the unknown variable kind of stuff. Okay. So remember I said it doesn't matter what the units are in here. The only thing that matters is that this has to be in Kelvin. So I'm going to add 273 to both of those. And you could do 0.15, like I said, or you, like your book does 273, but it's 273.15. It won't make that big of a difference. So that first one comes out to 298.
For our test, do you want the 0.15?
Nah, it doesn't matter.
Okay.
I will give it to you as the equation for the converting of temperature, I'll give it to you as 273.15. That will never be wrong. How's that? But I don't really care that much. In 1A, I care. In 1A, I'm like, you better use the 1.5 because you're going to have problems where you have that many sig figs and you have to worry about it. And this is 398 Kelvin. Okay. Because I added 100 more to it. And now I just have to plug stuff in. So I go V2 equals, and then I'm going to stick things. So the top one is V1, so that's 25 milliliters. What goes next? What's T2? The 398. And one of the problems that people have with this, they go, oh, there's that. Oh, there's the other temperature. And they plug in T1 instead of T2 because it's next to it on the table. But when you rearrange it, it's not next to it.
But if it's in Kelvin, you don't have to change it to liters, you can keep it as.
Yeah, milliliters doesn't matter. The answer will come out in milliliters.
Oh, so it doesn't.
Yeah, the only time you ever have to convert these guys over is when you do the ideal gas law. Okay. So 25,
Whenever you use R, basically.
3, anytime you use R, you're going to have to convert over. And then 298 Kelvin. Okay, so before I calculate, okay, what do you do with the temperature? What do you do with the temperature? I'm waiting for other people.
No, I'm sorry.
That's okay. What did we do with the temperature? Made it hotter, right? Got hotter. Went from 25 to 125. What does the volume of the gas do when you heat it? It expands. It gets bigger, right? So when we do this calculation, your volume better be bigger. And if it isn't, you plugged in T1 for T2 and T2 for T1, and it'll be smaller, right? That's like the only kind of way mathematically that people will screw this up, is they misinterpret the variables and they just plug in stuff and they make it an assignment that's wrong, and you end up getting an answer that's completely in the opposite direction. So I'm going to do 25, and I know this one's going to be bigger because it's 398 divided by 298. And I got 33.4. Let's call it 33 milliliters. I'm going to do centimeters cubed, milliliters. So I raised the temperature 100 degrees Celsius and it expanded to 33, okay? From 25 to 33. So that makes sense, right? And it's directly in proportion to the temperature change. And in fact, if you knew that, all you would have to do is have multiplied the 25 by the 398 over the 298 and not even worried about equations. Because it's, right, when pressure increases, or sorry, when temperature increases, right, volume increases. They're directly proportional to each other. So you could have done the proportionality of the temperatures and just multiplied that times your initial volume and gotten the answer, which is what the equation is. Okay. Okay.
The directly proportional part is the 398 over the 298.
Yeah. Yeah, this part is the directly proportional part. What I was talking about in the first part seemed kind of boring. Yeah. Okay, so this is what we're going to do. Take a short break, for the most part. So most of what we're going to do now is ideal gas law based. And this is tomorrow's experiment. So pay attention, kind of. Okay? Like think broad terms. I know you're getting tired. When you measure, if you want to know the molar mass of something, right? What are the units of molar mass? What's that?
It's the atomic mass.
It's atomic mass, but what are the units for molar mass? Grams per mole, right? So I'm going to say that molar mass, that's usually the symbol we give it, the big M, little m, is grams per mole. And that implies an equation. It's the m over the n, okay? And if you want to calculate the molar mass of something, all you have to do is weigh it, right? And then figure out how many moles you have. And a lot of science has been based on, a lot of old chemistry is based on, gee, how many moles do I have? And then they can calculate the molar mass because it's real easy to weigh something, okay? So this is, you have a sample of a gas. It's 827 milligrams. That's M, right? And its volume is 0.279 liters. At 88 degrees Celsius, What's that? Temperature. And 975 millimeters of mercury. Don't know why the pressure is that, but it is. Okay. Right? It's not a two-state problem. It's an ideal gas law problem. I can see that now because I've seen the table so many times. I can just see it filled out in my head. But if I have P, V, and T, right, and you know the ideal gas law is PV is equal to nRT, I have P, V, and T. R is always given. What can you figure out? Moles. Okay? So in order to get the molar mass of this unknown gas, all you need to do is have its mass and divide by moles. And in order to get the moles, because it doesn't depend on the identity of the gas, it doesn't depend on whether it's helium or nitrogen or whatever, right? All you need to know is the pressure, volume, and the temperature. So I'll explain to you how we do pressure in a second, how we normally do it. How do you think you get the volume of a container? Kind of a weird thought. Like most of the containers in lab, right, they have markings on the side and they say a volume, but that's not very accurate. If you want to know the volume inside like an Erlenmeyer flask, that's that weird TP-shaped flask. How would you figure out that volume on the inside?
Pressure from the outside?
No. Yes, too indirect. Fill it with water and pour it into a graduated cylinder, or fill it with water and weigh it. That's like actually the most accurate way to know how much water there is. But the graduated cylinder is pretty good. It's usually 3 sig figs. That's usually all you need. So like tomorrow when you do your experiment, if I remember right, one of the steps is you take an Erlenmeyer flask and you fill it with a gas, right? And then you need to know its volume. So when you want to know its volume, all you have to do is fill it with water, dump it in the graduated cylinder, and read the volume. Okay? Oh, I'm not recording, or I am recording. Oh, good, I recorded now. Okay, let's see. How do you know what the temperature of the gas is? Thermometer. Just measure it with a thermometer. Now we're going to do a trick tomorrow that makes it really easy. We're going to put the flask into boiling water. So what's the temperature of the flask if it's in boiling water?
100 degrees.
It's going to be 100 degrees. Eventually, it's not initially, it's not going to be, but it's going to take some time. It'll get to 100 degrees Celsius. So rather than sitting around trying to measure with the thermometer in the flask, we just measure the water temperature outside, and that tells us the temperature inside the flask eventually. So you measure that. Pressure, here's a harder one, okay? So I want to give you the concept on how we measure pressure inside a container. This is an Erlenmeyer flask, okay? And it's got gas in here, and you put a little hole in the top, okay? If the pressure on the outside is greater than the pressure on the inside, what will happen?
All the stuff that comes from the
Well, if the pressure on the outside is, well, yeah, it might break. But let's just say there's a hole in the flask, and the pressure outside is greater than the pressure inside. What's going to happen? Yeah, air will go in, right? But if the pressure on the outside is lower than the pressure on the inside, air will go out, or gas will come out. And the experiment that you're doing tomorrow, you're going to put a liquid in there, it's going to boil, and the gas is going to come out. How do you know that the pressure on the inside and the outside are the same?
air doesn't go in. Right?
Yeah, air doesn't go in and out. And the way you judge that is you put a little liquid on the top, or the liquid will just appear at the top, and you'll see bubbles coming out of the top. And when the bubbles stop coming out, that means the air is not moving in and out anymore. And then you know that the pressure inside the flask is the same as the pressure outside the flask. So you don't actually have to measure. As long as there's a hole in here, you don't have to measure the pressure on the inside. You just have to know what the room pressure is. And we have barometers in all the labs. And so you can just look at the barometer. It's going to tell you the number of inches or millimeters of mercury. I think their barometers might be doing inches right now. So I have to figure out how to change that. But the old school barometers that we used to have in every classroom was a big thing of mercury, right? And you would have to go up there, and the teacher would tell you not to knock it over. Every once in a while, one of those things would come off its hook and go crashing to the ground, and guess what happened? We shut the classroom down because mercury just goes everywhere, and then we have to clean it all up. Yeah, Nowadays, you bring what's called a hazmat crew in, and they clean that whole thing up. You shut the school down, and craziness. So we got rid of mercury. I used to have one in my office, but made me nervous. Okay, so what do I have to do here? Well, liters, right? I want to calculate moles, so I'm going to say N is equal to PV over RT. And then pressure has to be converted, right? So I'm just going to do it real quick. 975 millimeters of mercury (760 millimeters of mercury for every 1 atmosphere). So 975 divided by 760, 1.2829 atmospheres. What's my temperature? It's 88, so I got to go 88 plus 273.15, or not 0.15, it's up to you, 361.15. Everything else is good, right? The volume's in liters, isn't it? Oh, yeah? Yeah, it's in liters, so I just plug it in. So now I have my pressure. I have 1.2829 atmospheres. Volume is 0.279 liters. And R, 0.0826. Liters times atmospheres, internet slow, per mole times Kelvin. And the temperature, 361.15. And then I do that fancy calculation, hopefully get a really tiny number. Let's see. So 1.2 times 0.727, 0.279 divided by 0.08206 divided by 361.15. I get 0.1208. (0.01208) moles. Okay. So now to calculate the molar mass, I have to take the grams and divide it by the moles. So starting with my original problem, molar mass, I'm going to convert in my head. It's 0.27 grams, 0.827 grams. And the bottom I divide by 0.01208 moles. So 0.827 divided by, 68, let me just double check. 0.827 divided by 68.5? This comes out to 68.5. That's what the right number is, sig figs, by the way. Grams per mole. Okay, long problem, but it's actually two problems put together. So try to break these things down when you see them. when you're asked for a molar mass, right, it's grams per mole. Look for the grams in the question. Sometimes you have to subtract two masses to get the mass of something, right? And then the rest of it, if it doesn't give you moles, it's got to lead you somehow to moles to figure out the molar mass, okay? And then it becomes an ideal gas law problem. So the first problem was, hey, let's figure out what the molar mass is. Second problem is, well, we need to know moles, so let's figure out the moles are from the ideal gas law, and then just put them together. Lots of science is taking big problems and making little problems out of them. So it's kind of the process that you're doing here. You have a bigger problem. No individual part of the problem is hard. You've got to be able to put them together. Okay. Okay, I'm going to teach Dalton's law of partial pressures. Okay, I'm going to do one problem. Read the question, and I'll read it out loud. It says, if a container has 0.22 atmospheres of oxygen and 0.63 atmospheres of nitrogen and 0.06 atmospheres of helium, what is the total pressure? Okay. What do you think you do? Add them together. That's the answer. Just add them together. Yay, right? So you take 0.22 plus 0.63 plus 0.06, and you get 0.91. There'll probably be one, maybe two. Well, there's definitely going to be one. Okay, but let me give you the variations now. Now that I gave you the simple one, right? So pressure total, this is what Dalton said, is the pressure of, I'm going to write it out in equation form because that makes it look way more sciencey, plus the pressure of nitrogen, plus, sorry, the pen is not behaving well because the internet's slow, plus pressure of helium. That's kind of what you expect, and you get 0.91. So let me teach you a little bit about how this problem can be varied, but I'm not going to go into great detail because I think you'll figure it out. Let's say I gave you the total pressure and gave you the pressures of oxygen and helium and said, calculate the pressure of nitrogen. What would you do? Add the two together and subtract it away, right? This is by difference. What if I gave you, and this is the one that gets people, so I'm going to write this one out, okay? So same total pressure, okay? The pressure of oxygen is, I'm going to give you, it's the exact same number that's up there, 0.22 atmospheres. And the total pressure is, I'm going to give you the same number, 0.91 atmospheres. Calculate the combined pressure, and this is what, the wording is what confuses people. And then helium and nitrogen. Yeah, so how would you do that problem? Well, it sounds complicated because you got to calculate this combined pressure, right? It just means what are they together? You don't care what one is or the other. So all you have to do is say, oh, 0.91 subtract 0.22, and the rest of it is the combined pressure of the helium and nitrogen. Okay, it's just everything else. Okay. One of the things that's interesting about, any questions about that? You have some problems on the worksheet. You can do them. I didn't talk about it even this morning and told them to figure it out, and they figured it out. So it is, of course, because they're very bright. But they're like, is this all you do? I'm like, yes, that's all you do. I'm like, oh, Wow. Now, there's a very good reason why that was a big deal. Dalton's law of partial pressure is because when you mix volumes of two substances, they don't always add. Like 1 liter of alcohol and 1 liter of water, when you mix them together, you get like 1.9 liters of combined solution. Because the density changes, and the solution density changes, the total volume's not the same. So there's a reason why that was an important concept at one time. Okay. So one thing I wanted to mention is partial pressure determines the solubility of gas in a solution. So a couple of things about gas solubilities that I want to point out to you about pressure and temperature, okay? One is that pressure, or solubility, and I'm just going to call it S, is directly proportional to pressure. So if you have oxygen in a container and you double the pressure of oxygen above the liquid, okay, then you double the concentration of oxygen in the liquid. We talked about this in relationship to why people have to inhale HELOX, the mixture of helium and oxygen when they go really deep underwater, is because what that mixture is, it actually has less oxygen in it than regular air. So that when you go to high pressures, when you're diving deep underwater, you don't get an overdose of oxygen in your blood. It keeps the oxygen concentration from going above like the normal concentration, okay? The other thing that I wanted to point out is that the solubility of a gas is proportional to 1 over temperature, essentially. So as the temperature goes up, the solubility goes down. Now, it's not direct. It turns out it's not a direct proportionality thing, but it's that same general trend. At high temperature, the solubility of gas in a liquid is very low. So one of the things that they always tell you to do is, like if you have fish, right, and you have a fish tank, and you want to put city water into your fish tank, what do they tell you to do? There's 2 things. One is to treat it chemically to get rid of the chlorine. The other one is real simple. You boil it. You boil the water, and then you let it cool, and then you pour it into the fish tank, and then you pour the fish in it. But if you don't aerate the water, because when you boil the water and the temperature is really high, the solubility of gas is essentially 0. There's no oxygen in the water. Where do fish get their oxygen from? From the water. So if you take you boil water, and you cool it to room temperature real quickly, and then you throw goldfish in there, they'll suffocate. Because there's no air in the water. And it'll be at the top. It'll be that gulpy thing that they do, right? But if you aerate, so you have to aerate the water to get the oxygen levels back up in there. Okay. I'm going to skip the mole fraction thing because I don't think it's covered in this book.
You do that just by bubbling?
Bubble air through it with your aerator. Yeah, put it in the tank and bubble air through it. If there's already fish in there, though, and you dump in a bunch of oxygen-free water, it's not oxygen-free, right, because H2O, but it's O2-free. When you dump that in the water, with the rest of the water, you drop the oxygen concentration, you'll kill a lot of stuff in your tank. Okay. We do 1 stoichiometry problem and 1 cal problem. So I call it cal. Now, so collected over water. Did you guys notice how like humid it feels today? Why does it feel humid today? There's a lot of moisture in the air, right? What's the moisture? It's actually what? Gas, water, and the gas form. So part of the air that you're breathing right now actually has water vapor in it, okay? And using the same Dalton's law of partial pressure, the pressure of the air, or any gas collected in air, all right, is equal to the pressure of the gas plus the pressure caused by the water vapor. Now, there's not that much water vapor in the air that you're breathing right now. It's not displacing all the oxygen in it. You will not suffocate. Now, if you were in a closed room that had very high temperature, which would probably be enough to kill you, But if it was very high temperature, you could push enough oxygen out of the air that when you transferred that somewhere else, there wouldn't be enough oxygen in the air potentially, but I don't think that's going to ever happen. But the pressure, when you collect a gas and there's water present, the pressure of the gas that you collect is combined gas molecules of what you're trying to collect plus water vapor. And the thing that I wanted to point out to you is this, and you may know this intuitively, okay? This is a pot with water in it. And I'm heating it up. That's my fire. What does the temperature of the water do? It rises. What does the pressure of H2O do as the temperature of water rises?
Decrease.
Well, are you getting more? Like, think about like a pot, right? And you're heating it. And if you took the lid, like a glass lid, and you stuck it over a pot and before you heated it, and you looked at the lid, there'd be no water on it, right? But as you heat it, what do you eventually see forming on the pot? It starts to shake. That's from gas being created, but you see water condensing on it, right? So what is it telling you about the concentration of water in the air and when it's hot? It's much higher, much higher. And it's collecting on the cold surfaces. That's why you can see the liquid, but the gas vapor itself is clear. That's why when you take a pot and you lift it off, right, the boiling water, and you got a lid on it, and then when you pull it off, what follows the lid? A bunch of steam, right? And you guys that don't cook, you could just go home and boil water, and you'll see all these things, right? But when you pull the lid off, all you see is all this water, that steam, right, coming off the lid as you're opening. Why is it doing this? Because in the pot, it's cool. I mean, it's hot, right? And when you lift the lid off, the temperature drops suddenly, and it literally forms droplets of water as you remove the lid. Okay? So all of that gas that you're seeing was clear in the lid above the liquid in the pot, but when you cooled it down, it condensed, so now you're seeing it. Okay? So the point, though, that I'm trying to make is that how much water vapor is in the air above the liquid just depends on temperature. Okay? So if I make a graph out of this, it looks something like this. I'm going to put 0 down here, and I'm going to make 100 degrees here. So what does water do at 100 degrees? It boils, right? It does that. Make this, I'm trying to make this a little more accurate, but I kind of just missed it. Let me do this. Let me redraw my curve just a little bit. So that's where the water boils, right? 100 degrees. And this is the pressure. This is the temperature at the bottom. What do you think this pressure is at 100 degrees? It's higher than when it was let down here. But there's actually a number. You can know this pressure anywhere you're at.
It's like the altitude of where you are.
Yeah, but what is it generally? What is it generally? Yeah, generally it's the atmospheric pressure. It's usually about 1 atmosphere. So that leads the question, like when you're looking at the pot and it starts to boil, what do you actually, okay, think about this. There's a bubble that forms at the bottom of the liquid. What's in that bubble? Not oxygen, not hydrogen by itself, just water vapor. All right, now think about the pressure on top of the pot. This pressure is about 1 atmosphere, right? And in order to make a bubble in the liquid, the pressure, the vapor pressure, or the pressure of the water vapor, that's that number there, has to slightly exceed 1 atmosphere to push a hole into the liquid. So it's literally down at the bottom, you're heating it, a couple of water molecules get enough energy, they split the liquid apart, and they fill it with water vapor. So when it comes out and it pops, right, literally it's just, when it pops, there's no air in there, it's just water vapor. Okay? And it can only boil if the temperature is high enough to create a pressure on top of the liquid that's above the atmospheric pressure slightly. Okay? So sea level, where we're at roughly, it boils at 100 degrees Celsius. Because the pressure that's holding the bubbles down, okay, is 1 atmosphere. So we call that the normal boiling point of water. If you go really high, let's say you go to, I talked to somebody about this the other day. If you go to Rocky Mountain National Park, for example, like one of my favorite places to take that hike all the way to the top, it's just like a gorgeous view. Anyways, water boils at about 90 degrees Celsius. Right? Why does it do that? Because the pressure up there is much less than 1 atmosphere. And so in order to make the little bubbles in the liquid, you don't need as much energy. So you only have to get it up to about 90 degrees Celsius before the bubbles start forming. Okay? So anybody ever, this is about 90. Anybody ever go camping and try to make spaghetti? Like high altitude and then try to cook spaghetti? Yeah. So you take an aluminum pot and you take like pasta with you. You get water out of the stream, or you have one of the, now that you have those water filtered thingies, but you're boiling it, so it doesn't matter if there's a cow turd in it, really. Okay. So you take take the water out and you boil it and you put your pasta in it. You know what happens to it? It turns into mush, and it doesn't cook the way it does at lower altitude. Because at high altitude, you're cooking it at 90 degrees instead of 100. The 10-degree temperature difference makes it a lot longer to cook. So by the time the pasta cooks, it turns into mush instead of spaghetti, and you're eating this weird spaghetti slurry thing with water that has boiled cow turds in it. It's the best, though. When you're hungry, you'll eat anything, right? We used to intentionally go up with pats of butter and aluminum foil and a cup like a baked potato. And we would go up for 3 or 4 days, some baked potatoes in foil. Because the deal is you were going to catch a fish and cook it. If you didn't catch a fish and cook it, you ate potatoes and you went hungry. So we found things to eat. This is when I was a scout. This was many years ago. All good times. So anyways, the point is, pressure of water goes up in a predictable way with temperature, okay? So now what we're going to do is we're going to do a problem based on this, and I am just going to skip down to this. I may not have quite enough time to do this, so what I'm going to do is I'm going to do the last part of this problem. Okay. And I'm going to delete some space in here. And I call it a cow version because cow stands for collected over water. So when you have a reaction and you're collecting a gas from over water, right, you have to consider the water vapor pressure. So you have zinc and HCl reacting to make zinc chloride and H2 gas. Okay? And then we're going to do this version. 325 milliliters of hydrogen gas is collected over water. That's the cow part. At 25 degrees Celsius and 748 millimeters of mercury. How many moles of zinc react? And then they give you this information here, the pressure of water at 25 degrees Celsius. Okay? So let me show you how you take this into account. Okay? They're saying the following. I'm going to write out my volume, right? 325 milliliters. My temperature is 25 degrees Celsius. And my pressure, must be up in Kings Canyon doing this experiment, 748 millimeters of mercury, or mama huggas. Right? And that's hydrogen gas, it's H2. So this is for H2. Now, because it's collected over water, this 748 millimeters of mercury is not all hydrogen. Okay? And this is an ideal gas law problem. I have pressure, temperature, and volume. What can I calculate from that? I can get moles because it's PV equals nRT, right? So I have the pressure, I have the volume, R is a given, I have the temperature, so I can calculate moles. But the problem is this isn't just hydrogen. It's hydrogen in water because I collected it over water. So in order to get the pressure of hydrogen, just subtract the pressure of the water. So I have pressure of 748. Minus, and then you have to be given this number, by the way, 23.8. There's large tables of it, or you can actually get like a little app that calculates the value for you at every temperature. But that has to be given, 23.8. Okay, so I'm just going to give you the scheme of things because we're almost out of time and I want to finish on time. All right. This is going to be the pressure of hydrogen. This is the temperature of hydrogen. This is the volume of hydrogen. You can calculate the moles of hydrogen. And then once you have moles of hydrogen, you can calculate moles of zinc because it's 1 mole of hydrogen for every mole of zinc, and then convert it to mass using molar mass. Okay? So it's a stoichiometry problem after that. But lots of these gas, you're going to see versions of this kind of problem on the exam where I give you some quantities of gas collected and say how many moles of this reacted. The gas law part is PV equals nRT, calculate moles, and then the rest of it's a stoichiometry problem from the last chapters, okay? All
Are you
right.
gonna give us the equations on the exam?
The balance equations?
No, are you gonna give us these?
Pufner?
E equals nRT, are you
Yeah.
gonna give us the equations, okay.
I think they may have actually even been on the last exams. Yeah,
We just didn't know what they were yet.
yeah, we just didn't cover them yet.